Hello, everybody. In this lecture, I shall discuss with you how we can use Scipy in linear and nonlinear regression. Here we have to call Scipy optimize, then we call curve fit function, through which we can carry out linear regression, and we shall also discuss with you how we can use Scipy with poly-fit function also in order to realize non-linear regression when necessary. As I found it, really, working with Scipy is simple and maybe simpler than working with OLS or with gradient descent. All what you have to do is to supply the arrays of the independent variable and the dependent variable also. Then we have to call the Scipy optimize curve fit. Then we have to pass to the curve fit the model function and the independent and dependent variables data. And that's it. When you use curve fit, it gives you possibility to have information about the parameters, optimal values, which here the values of the coefficients of the linear fit, and also the parameters covariance matrix through which you can estimate the standard error values for the coefficient A and for the coefficient B. If you want to arrange it in steps, you can say that at first we have to import the curve fit function from Scipy. Then we create a list of NumPy array of the independent variables. The same thing we do with the data of the dependent variables. In this case, sometimes we need to import the necessary data from a given URL location. We shall do this in the next example. And after that, yes, we define the equation of the model, the type of the model which we are going to use. Generally, we are working now with linear model. And then we use the curve fit. And after that, we pass through the curve fit the required arguments like the model equation or the model name here, and the values of dependent and independent variables. At the end, we extract the values, which is the parameters optimal value and the parameters covariance matrix. So as a beginning, when working with Scipy, we need to import from Scipy the optimize function, and from it we import curve fit function. From Scipy dot optimize, this is an attribute of Scipy, and from optimize we import curve fit function. We import NumPy as NP in order to work with arrays, and we import matplotlib in order to draw the scatter plot or to plot the linear regression line over the scatter plot. Okay, so these are now imported. We now define the model, which represents the trend of the scatter plot. Here it is called linear model, so we are going to work with a linear fit. The variables of this function are x, which is the independent variable, a and b are the coefficients, the slope and the intercept. The relation between these three arguments are a multiplied by x plus b. This is the equation of the line of regression. X here is given as a list beginning from 0 to 5. And the dependent variable is given these values beginning from 25 and ending with 0. Of course, the y values could be selected randomly. And now having the dependent variable y and the independent variable x and the name of the model itself, so we can pass these values to the curve fit. So curve fit, now we pass the name, linear model, x and y, and with this, we are now able to get the p-opt, which is the parameters optimal values, and the parameters covariance matrix. We can print them directly, so print p-opt and print p-cov will give you these values. P-opt, this is the parameters or the values of the coefficients of the linear fit, A and B, and this is the matrix which represents the covariance between the variables. And here, as you see, this in the this diagonal represents the self-covariance of x, and this is the self-covariance of y. If you want, here, as you see, p-opt is given as a list. You can separate them and have A alone separately and have the B value alone. What you are going to do, you take the popt and slice from it the first element, which is indexed 0 here, it is A, and popt with an index 1 is B, and then you can print A and B, and you get the value of A, which is -4. Here it is again, A is -4.94, for example, and B is the other value, which is 23.19, which is this value. No, this is just to show you that how you can get them separately. Now, in order to plot the scatter plot and to plot the predicting or the regression line, here we used a range function from NumPy a range between two values, -1 to 6, with a step of 0.1. This will be about 6 values here. The equation of the regression line y predict is equal to A multiplied by x. A is the slope here. And because we get the slope negative -4.9 here, we write, okay, now it's in a general form, it's given plus b, no problem. The plus becomes minus, no problem. And now, to plot the first line here, x is known to us, y is known to us. They are given in the lists here. and we assign for them a red dots O as a dot, and we get this is the representation of the scatter plot or the points plot. In order to plot the line, we use the X predict and the Y predict values, and we assign for them a color blue, and we get this line. And that's it. These drawings may be necessary and may not be necessary, but as you see, you directly find the values of POPT and PCOV, P covariance, and the problem is solved. Really, this is a very simple example, just to show you the technique and how we can work with Scipy. Now I shall consider with you, illustrate to you another example where the data X and Y, which is the dependent and independent variables, are not very clear. They are given within the data saved in a file type CSV. CSV file, comma, separated values file. This is usually done because in order to save memory space, and this is the URL here given in the site here where this data file exists. So what we have to do, we must, of course, read the data which is in this CSV file and extract from this data the X independent values and the Y dependent values and continue our work accordingly. In order to read the CSV file, we use NumPy. We use the data frame, read CSV function, read C underscore CSV function. To read a CSV function here it is already from pandas imported as read CSV. So this function now exists. We can use it directly, and also for plotting the required curves, maybe we need a range function. From NumPy, we imported a range. So we have the read CSV function available. So read CSV function is available. We pass to this function the URL name. So these values now are given. Header we do not need, are none. So now we can get a data which is called the data frame. We do not know in advance the number of rows and the number of columns existing. So for any case, to have an idea about this CSV file data, we print only the first 5 rows. The first 5 rows by calling the head function from the data frame. So we print the data frame, which is the data here already existing, which we have it, but we need only the first 5 rows, so we print dot head function. This expression gives you 5 rows with the specific number of columns. If you look at it here, this is the data frame head, 0, 1, 2, 3, 4. This is the 5 rows, and these are the columns associated with the CSV file. But this is now not a CSV file. Now, by using the data frame, it is converted to a data frame. So as you see, we have here labels for a label for each or index for each column. 0, this is the 0, 1, 2, 3, 4, 5, 6. And this is also the indexes of the rows from 0 to 4. Of course, they continue down to the last row number. Sometimes you do not need to have these labels and these indexes, and you need only to have the data itself. This is possible here to do by extracting the data only and leaving these labels and indexes. How this is done? We take the data frame with the attribute values. Data frame dot values. Now we have a data, we call it data. This data now is the same values which are here, but without these headers and these indexes. Here it is 8.3, 8.8, 8.2. Here I limited the number of rows to 3 only. So you can see this here. That is, it is really limited to 3. Here the data is, this is the number of rows from 0 to 3 and the number of columns from 0 to 7, because they are 6 beginning from 0 became 7. So we have printed the data, and now we have an idea how we can extract or slice the data by using the attribute values. Okay. Now we want to extract from this data the X and the Y data. Here, as you see, I have taken the data and selected from it all the X values with the fourth column, the fourth index column, and also all the data, another column, all the data, all the rows of the data with the last column. So if we go to this data, this is 0, 1, 2, 3, 4. This is the fourth column. So we want to use this column data as the X independent variables. And the last column, which is indexed -1, or here it is indexed 5, 0, 1, 2, 3, 4, 5, 6. So, and this last column data will be used in our case as the dependent variables. So now these data are given, printed. The X variables begins from 107, as you see here, and it continues up to the end, from here up to here. Now you can find that 0, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 values. The rows of this data set are 16, and the values of the Y are given here also. They should be also 16. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, which is 0 from 0 to 15, 16. So we have now the values of X and Y. Now we know the values of X and Y, and X and Y, so we can use them and pass them to the curve fit function. So now we can use the curve fit function because it is imported already. We pass there the name of the title of the objective or the model itself. Here it is given objective. It is the name of the model, linear model. This is the X independent variable, and this is the Y independent variable. So now we can get the POPT and PCOV, the parameters optimal values, which is the slope and the intercept, and the covariance matrix values. Here, I did not print them alone, but I have worked out the POPT to be considered as A and B. And now I have printed A and B. So we can get the values of A and B. And also we have printed the value of the covariance matrix. If you look here, this is A and B. This is the value of A. This is the intercept. No, this is the slope. And this is the intercept. Knowing these values, now we can have an idea about the prediction line equation, which is equal to this value multiplied by X plus this value. The covariance matrix, as you see, is given here alone. Now, if we want to plot the data set and the line itself, this is also possible. We have done this previously. So, as you see, we have created an array which represents the X points here. We used np dot line space, beginning from np minimum value of X and np maximum value of X. And we have required, we wanted 16 values. So now we have 16 dots or 16 values of the X value. Accordingly, now we will have Y line, which is also 16 values. It is defined as the objective of X line and the value of the slope and the value of the intercept. So now we know X line and Y line. We can plot it. The plot here is given as dashes with a color red so that we can distinguish it from the plot scatter X and Y. The scatter X and Y is these blue dots, and this dashed red line is the linear regression line. Now I can say that what we have done now is very similar to what we have done in the previous example, except that the data which we dealt with is given through a URL where the data file is located, and we read the data by using data frame read CSV, and then we extracted the data and extracted or sliced from there the X and Y variables, and then we used, as usual, as we have done in the previous example, by passing the values of X and Y and the model name to the curve fit. What else here? Here I have shown you, I am showing you here how we can estimate the performance of the curve fit. This is done differently, but for me, really, it is maybe one of the shortest and smartest ways to do that. From another point of view, I wanted to introduce to you gradually the library of sklearn. So sklearn is a library which you inevitably are going to use when working with machine learning and deep learning. we have import the sklearn. Sklearn already installed in the computer. You can go to the maybe to the PC, for example, to the C, to the users, then I have downloaded from Anaconda 3. This is Anaconda 3. And there you will find packages. This is the packages which are included in Anaconda 3. There you will find sklearn, B, C, D, E, F, G, H, I, J, L, M, N, O, P, R, Q, R, S. Now S. S, M, S, K. It should be somewhere. SK here. It is SK image, sklearn. This is the library sklearn version 1.4.2, which was downloaded from Anaconda. Now I have imported the sklearn. Sklearn, from sklearn, I called the matrices and imported from there R2 score. This R2 score really is a function which works out the result, which is called the R squared. Remember, we have met with R squared previously when we estimated the performance of the OLS, and also we have met this expression when we have worked with LabVIEW. To generate the R squared value, we need to import R2 score. R2 score now, we pass through values the true value Y and the estimated or predicted value, which is here in our case Y line. We get as the output the R squared value. If you print it here, I printed the R squared in two different ways, and it gave me these results. R squared is 9.22, 0.9, and the other case also the same 0.9. This means really this is a very accurate work and high percentage because it's very close to 1, and there is no problem with our work. This is some kind of testing the algorithm of the curve fit and how the curve fit works. It works well. You remember when we worked with OLS, it was about 0.83. Now it is 0.9. It is really a very high percentage and very acceptable result. Also, if you look at the matrix, the covariance matrix here, and this is the self matrix of A, and this is the self matrix, self covariance of A, and this is the self covariance of B. So what do you need is to take the square root of this value, and then you will get the standard error, and the square root of this value, and you get the standard error. Really, I have done this by hand, and then I have done it also as programmatically, and the results are found to be the same. Programmatically, from NPy, you call the square root of the NPy diagonal P covariance. And you have to find the square root of this value and this value, which are existing at the diagonal of the P covariance. If you do that, you will get the square error. The square error here is for A and for B. So square error with index 0 gives you square error for A. Square error with index 1 gives you square error for B. And if you look at them, they are also given here. The standard error of A is equal. This is the error value. It is very high percentage really. But this value of B somehow with a higher error value. But this is the case which we have. So as you see, to summarize what is there, there is nothing difficult here. Everything is clear. You shall be accustomed to work with the URL and how to read the CSV files by using Python, and we shall give you an idea in the coming example how to do it with LabVIEW also, and then how to extract the data from the data frame and how to extract the columns representing the X and Y, the dependent and independent values. And after having the dependent and independent values, practically, you have to call the curve fit and pass there the necessary arguments, and you will get the outputs POPT and PCOV. In order to test the results of the function here, the regression function or the curve function here, you have to find, as I told, the R squared value. The R squared value, if you understand what I have shown to you by using sklearn, you can repeat this always with any other example and have an idea about the tolerance of this work. Also, you can make use of the covariance matrix and take the square root of the diagonal values and get the values of the standard errors. So this is the second example now shown to you. We shall work with another example here, very interesting example, which uses the polynomial fit, NP polynomial fit. This is also a Scipy function which could be used to find the coefficients, specifically when the degree of the model itself is not equal to 1 but higher than 1. In this case, the coefficients will be 3 or 4 or 5, and we have to use the polyfit instead of using the curve fit. Curve fit practically and polyfit with an order equal to 1 give the same results. But if you want to use polyfit with an order or degree higher than 1, then we are working with nonlinear regression. Here is an example I am giving you and illustrating with you this fact. So we have imported NumPy as NP in order to work with arrays, and we have imported matplotlib in order to make plots. I have taken the values, exactly the same values, x and y, which were extracted in the previous example. I took them as 2, as you see here, values, and this is the independent list which represents x, and this is the dependent list which represents the y. What is there? So what you need to do is only to call from NPy polyfit, NPy.polyfit, and pass there the variables x and y, and define here the order of the polyfit function. If it is 1 as written here, this means that we are making a linear fit. As a result of that, we shall get here the coefficients. Let me take away this hash from here and put it in front of the second line here. Now this is working. X is known, y is known, and the degree of the polynomial is 1. So we are working with a linear fit. And we are asking now the program to print the coefficients, these coefficients of the linear fit. There will be two only. One of them which is the slope, and the other is the intercept. Now we shall see them. If you look at the curve here, it is not linear. Now, because I am using 1, I shall run the program, and you shall see that it has changed to linear, completely linear, and you have the coefficients shown as 2 values, and this is the equation of the model of regression here, which is this coefficient multiplied by x plus the intercept, normal. But, of course, sometimes you feel that the distribution of the initial set is not that linear, and maybe it is better to approximate the model to be a polynomial of a second degree, or of a third degree, or of a fifth degree, and so on. This is also could be shown here. So I will put the hash here now up again, and take away the hash from the down one. And now the program contains the same thing, numpy polyfit xy, but the degree now I have taken it 3. So now we shall have 4 coefficients. Print coefficients, we will have 4 coefficients. If we run the program now, look how it is now extending, and the values of the coefficients now 1, 2, 3, 4. This is the equation which represents the polynomial. Here, really, we can do it easily. The polynomial is equal to, or is assigned as NP, polynomial 3D coefficients instead of 1D, 3D, because we are doing there. It could be 1D, this is just a name here. And in order to plot the dots here, we use the plot scatter XY. They are given blue always, because I didn't define another color. And now we plot X and P of X, which is the red line here, color red, and that's it. So everything is shown and clear. Suppose we want to have the order of the polyfit equal to 2. So now we shall have a 3 coefficients instead of 4 coefficients, and the curve, of course, will change a little bit. And now, if you look, this is the curve which we have achieved, and these are the 3 coefficients of the polynomial, and this is the equation also of the new polynomial curve. As you see, working with Scipy, it seems to me, is standard and direct forward. There is no problems. It doesn't require specific preparations. I think it could be recommended to be used by you without any problems. Okay, now we have done 3 things. I have introduced you to the curve fit by using Scipy with a simple example. Then in the second example, I have shown you how we can manage the URL of the file of the type CSV and how we can read the data there and extract the data and the columns representing the dependent and independent variables. Also, I have shown you there how we can find the R squared and the standard errors of the coefficients. In the third example, I have introduced you to the as you see, polyfit function, also of Scipy, and we have also illustrated to you how it works. Now I shall leave Python and go to LabVIEW to illustrate to you similar examples solved by using LabVIEW. Okay, so I now go away from this page and go to LabVIEW. Now I shall go to example, which is solving the same data set which we used in the second example, which used the same URL and the same data which was included in the CSV file. Okay, don't be afraid. Don't look at the picture here. It is really a very beautiful picture. There's nothing complex. And I will explain to you how we do it. So we have the URL. This is the URL value. If I double click it, it is here. This is the URL which was used in the second example of Python. I use this URL to get the data value without the rows and without the labels. This is called the body of data, the data body. This is done by using the get.VI. From where to have it? This get.VI, if you right-click this block diagram and go to data communication, and from there you go to protocols, and from protocols you go to HTTP client, you will find here this get.VI. You can, I put it here for you. I go to the help to show you. And now here it is. This is the function get.VI or the VI. It requires from you the URL. And it gives you the output. The headers, if you need them, I don't need the headers. The body. The body is the data included in the CSV file. So, if I go out, what I have done, I have taken the output here, which is the body. Look at it now. Body. This is the body. If you double click it, it is this data here. This data here is the same, still a CSV file. The values here are separated by commas as they are, and the number of rows will be 16, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 16 as it was, and the number of labels will be, as I remember, 7. 1, 2, 3, 4, 5. Let me see. 1, 2, 3, 4, 5, 6, which are 7. Now, this data, which is a CSV file, must be converted to a data frame by using the pandas library. How this is done here? Okay. Now, before working with this data, with this body, this is the CSV file, this data now is written to a file in the computer. This is the address of the file. It is located in the documents longly when its name is longly one. So what we have done here, or what we have to do, as you see, we have just saved the CSV file in the documents. Don't look at this broken here. This is because I have put this here. If I take it away, it will be okay. Now, what we have done, we use again another function so that we can read the CSV file without commas. Read delimited spreadsheet VI. Where this is and how to work with it. You right-click it. Okay, no need to right-click it. You right-click here, and then you go to the input-output here, and from input here, read delimited spreadsheet VI. This is the function with glasses, as you see, is the same as this one. By using this function here, it requires the path. The path. Here is the path where I have saved it before. So now the path is known to us. And now at the output, here I have two-dimensional array with the values, but now it will not be, here must be a constant with comma, separating comma, and this is the all arrays, as you see, all arrays set up here, which are the values which is here represented as a data frame, but without commas. Exactly the same. The last one is, I'm sorry, 1169. Here is 7551, the same. This data here is the same data here, but now it is represented as a data frame. From this data frame, I want to make use of the dependent and independent values. So I have extracted here, if you take it up to be seen, I have taken this column as a, this is optional because I want to take the same data which was used in the previous example. So I have taken this column as the X independent values and the last value which was there as the dependent variable. Here they are. This is the X value and this is the Y value. How they are done, I have extracted them by using the index array. So this is the two-dimensional array, two lines as you see here. This two-dimensional array now, I use the indexed array. And I indexed here the column, the fourth column. And here I index the sixth column. How? Let's go back. This is the fourth column. 0, 1, 2, 3, 4. This is the fourth column. And this is the sixth column. I have extracted them by using the index function. This is the index array. This is another index array. And now I have X here and I have Y here. X is this, the column which is here, and Y is the column which is here. But for the, I am not interested only in showing them. I want to use the X and Y. So I use the X, the independent variable, and the Y independent variable for further work. What is there now? Now I am repeating the example which I have shown you in the previous, in one of the previous lectures, where we used general linear fit.VI in LabVIEW. And I remember I told you that this function works practically as a copy of the OLC. And in the OLC, you remember there was a necessary step to do in Python, yes, which is add constant of x. I told you that we can do, this is the two, or here it is called the h function. If you look at this point, you will find h. And this h input here is practically an initialized x array with added ones against each of the items, and then it is transposed. I have explained this to you previously in a previous example when we used the general linear fit VI. So at the output here, we expect to have the best fit. I mean, we expect here to have the, okay, it is not shown. Let me show it to you. Not bad to show it to you. Okay, now create indicator. This is the best fit. Now, if you look here where it is, here it is. Now I shall open it for you. And now if I run the program, it will give you the values which represent the best fit. We have done this before. Okay, so now we have the best fit value, but I am not intending to see it or to show it to you only. I want you to use it, so it is used here by building an array, another two-dimensional array. One of them is the original y, so that to show or to draw the original y and to draw the predicted y and to show you how they are related to each other here. This is the points, which is the original, and this is in red is the predicted values by this function. Now, when we go back, also I have also taken both the predicted value, as you remember, and the original value, and fed them to the goodness of fit VI to get the R square. And the R square here also, as you see, is given, remember, 0.92. In the previous case, when we solved the same problem by using sklearn, it was also about 0.92. It is exactly the same answers, exactly the same performance accuracy, nothing different. What about the coefficients? Here are the coefficients. This is the slope 0.4848, and this is the intercept, and these are exactly the same values which we have got before. This two-dimensional array is the H array, which is, as you see, includes this column of ones, and these the values of X column. It is these values here which are fed to the function. And the last thing which I want to remind you with is here is a trial just to show you how we can write the equation of the regression which we have done. And also this was explained to you, the equation, the equation is given maybe downwards. Let me see where it is. Here it is. Y is equal to the slope, which is 4848, multiplied by x1 plus 8.38, which is the intercept. X2 here is equal to 0. We are working with a linear regression. We are not working with a polynomial fit. So, as you see here, the work also is practically the same analogy which we have done by using Python. We need to read the CSV file and save it somewhere in the computer, then convert it to a data frame with rows and columns. Then we select the columns of interest, which represent the dependent and independent values. And then we introduce these values to the regression function, which we are using. In this case, we are using the general linear fit. So they are introduced to this function. And at the end, we get the best fit values. And we made use of these values for drawing of the received values and for estimating of the goodness of the fit VI. Okay, this is a question which I aim to explain to you. I have also another interesting example related to what I have explained in Python. I want to show you also, which is this one here. It will not take that much time, but it is related to the implementation of polynomial fit by using LabVIEW. Because now we have used the linear regression in this example, and we did not use the polynomial fit. So now I shall use it also to show you how we can work with it. Look, we have extracted two columns from the data frame, one of them which represents the x values and one represents the y. These are the x values and these are the y values. These are the independent values and these are the dependent values, and which are usually used to be fed to the polynomial fit. So if we go to the block diagram here, we find that this is the x. If I double click it, this is the x input values, and the other one here is the y input value, where they are input to the general polynomial fit value. How it comes, from where it comes, it is easy. Right click on the block diagram, go to the mathematics, go to the fittings, and now you will find polynomial fit. This is the general polynomial fit VI, which we are working now with. Okay, so we can do it directly then. So we have fed the independent and dependent variable. Here in this input, we have created least square method to be used. If it is not clear for you, I can cancel it. Look, and now newly created for you. I have to go to this terminal, right click, create constant. Now you can select between the options you have, either the least absolute residual or by the square. I left it least square. And now at the output, I have the polynomial coefficients directly. The polynomial coefficients, here they are. This is for a degree of 3. The polynomial degree here is 3. Let us go and check it. If you go here, yes, this is the polynomial fit. Here, this is the terminal polynomial order. I have put it 3. If you put it 3, as it is there, you will get 4 coefficients. And this is the presentation of the original true values. And this is the regression fit, polynomial fit with an order of 3. If the values in white here, which are existing on this line, are those values which are called best polynomial fit. So if you go back here, you will see what I have done. I have just taken x and y And in order to plot these red dot points which represent the true values, and I have taken the output with the input here to represent the XY graph. It is represented here alone. This is the predicted value alone. These points now here are those red values alone. Now I have assembled them together. This is just to show you. I have assembled them together in one XY, in one XY plot here, XY graph. Here it is. And concerning the accuracy and the performance of the program, also I have put here the goodness fit.VI, and as you see, the value of R squared here is also about 9.94, very high percentage, very high accuracy of this work. So as I feel here, everything is clear. I think I have explained to you all the details required. What is needed by you is to read this lecture once or twice, and so as to remember the basic steps and to remember some interesting points for you. And with this, we finish this lecture and see you in the coming lecture, and goodbye.